This video will introduce you to the 737NG bleed air system. We'll see its purpose and operational characteristics for a typical flight. We'll also see where to attach test equipment and some common troubleshooting examples. Before we get started, remember, this video is for training purposes only. It does not supersede or take the place of any written documents of your company, the Boeing Company, or any regulatory agencies. For the most complete and up-to-date information, always see the Aircraft Maintenance Manual, or AMM, before beginning any maintenance procedure. Also, be sure to know and follow all safety precautions. And finally, keep in mind that all pressure and temperature values mentioned in this program will be nominal. For actual pressures and temperatures, see your AMM. The 737 bleed air system supplies engine compressor air for wing and engine inlet cowl de-icing to the air conditioning packs for air conditioning and cabin pressurization, and for nitrogen generation system operation. The system uses 9th stage air during its low power settings and 5th stage air during higher power settings. Note that bleed air is extremely hot and must be cooled before being sent to the AC packs. The pre-cooler is an air-to-air heat exchanger that uses engine fan air to cool the bleed air. Note that the system is controlled using a series of valves, temperature sensors, and pressure sensors. The high stage valve, or HSV, and the pressure regulating and shutoff valve, or PRSOV, work together to control bleed air pressure. And the PRSOV and the pre-cooler control valve, or PCCV, work together to control bleed air temperature. In the HSV and PRSOV, control air enters the valve actuator and is opposed by downstream pressure. The control pressure tends to force the valve open, and the downstream pressure tends to force the valve closed. So the position of the valve is the result of the force balance between the control pressure and the downstream pressure. Note that for both of these valves, the normal or relaxed state of the valve is to be closed. The PCCV is different in that control pressure is used to close the valve. Since the normal or relaxed state for the PCCV is open, reducing the control pressure to the PCCV allows the valve to open. As we have seen, the system uses either 9th stage air or 5th stage air during different phases of operation. The flow of 9th stage air is controlled by the high stage valve and the high stage regulator, or HSR. Together, the HSR and HSV control 9th stage air to supply 9th stage air for low engine speed operation, regulate the pressure of 9th stage air to 32 psi, shut off 9th stage air during high engine speed operation, and prevent reverse flow into the 9th stage. Bleed air pressure is controlled by the pressure regulating and shutoff valve, or PRSOV, and the PRSOV is controlled by the bleed air regulator. Together they regulate bleed air pressure to 42 psi, prevent overpressure in the system, and in concert with the 450 sensor, prevent runaway over temperature. The pre-cooler control valve, or PCCV, regulates the amount of fan air to the pre-cooler to regulate bleed air temperature. Now that we've seen that the HSV, PRSOV, and the PCCV control airflow through the system, let's take a closer look at how each of these valves is controlled. When the engine starts, the HSV is closed. As pressure reaches 10 psi, the HSV is fully open. Note that the HSR regulates the HSV control pressure to 16 psi. When the downstream pressure is more than 32 psi, it overcomes the 16 psi control pressure, causing the HSV to move toward the closed position. This balance of forces regulates the 9th stage pressure in the system to 32 psi. If the ninth stage supply pressure goes to more than 110 psi, the overpressure function of the HSR cuts off pressure to the HSR to prevent damage. Note that during engine start, reverse flow can occur. When this happens, pressure from the downstream sense line causes the HSR to remove control pressure from the HSV, which in turn causes the HSV to close, preventing reverse flow to the ninth stage. As engine speed increases, fifth stage pressure will increase. When the fifth stage pressure reaches 32 psi, it will overcome the check valve and flow into the duct. This will cause duct pressure to increase beyond the ninth stage regulated pressure of 32 psi, causing the HSV to close. The bleed air system is now operating using fifth stage air. Note that the check valve prevents reverse flow into the fifth stage when duct pressure is higher than fifth stage pressure. Now let's look at the operation of the PRSOV. Remember that the PRSOV and the bleed air regulator work together to control the bleed air system pressure. When the engine starts, the PRSOV is closed. As pressure reaches 10 psi, the PRSOV is fully open. Note the bleed air regulator regulates the control air to the PRSOV to 24 psi. This is enough to overcome the downstream sense air to the PRSOV and to keep the valve open. As engine speed increases even further, the PRSOV will regulate the duct pressure to 42 psi. If the HSV fails and allows extremely high pressure into the bleed air system, the overpressure switch in the bleed air regulator will cause the PRSOV to close. Note the overpressure switch will also cause the bleed trip light in the flight deck to come on. Now that we've seen how the bleed air system controls pressure, let's see how it controls temperature. As we saw earlier, the pre-cooler is an air-to-air heat exchanger that uses engine fan air to cool the bleed air. The pre-cooler control valve, or PCCV, and the 390 sensor control fan air to the pre-cooler. When the engine starts, the PCCV is open. As the pressure rises above 10 psi, the PCCV starts to close. As engine speed increases, so does the bleed air temperature. When bleed air temperature reaches 390 degrees Fahrenheit, the 390 sensor begins to open, reducing control air pressure. This causes the PCCV to open. When the bleed air temperature reaches 440 degrees Fahrenheit, the sensor will be fully open, causing the PCCV to be fully open. As conditions change, the sensor will change the amount of control air vented, and the PCCV will open or close as needed. If the PCCV cannot provide enough cooling air, the system can also use the PRSOV to control temperature. If system temperature reaches 450 degrees Fahrenheit, the 450 sensor will open. This reduces the control air to the PRSOV, causing it to move toward the close position. This reduces the amount of bleed air flowing through the pre-cooler. With less hot air flowing through the pre-cooler can reduce the temperature of that air more effectively. If temperatures continue to rise, the 450 sensor will open fully, causing the PRSOV to move further toward the close position. This reduces the pressure further, protecting the air conditioning packs and wing leading edge from extremely high temperatures. If the temperature reaches 490 degrees Fahrenheit, the 490 over temperature switch will close the PRSOV and the bleed trip light will come on. In summary, the purpose of the 737NG bleed air system is to determine whether the system uses ninth stage air or fifth stage air to meet system requirements, regulate engine bleed air pressure, regulate bleed air temperature, prevent reverse flow into the engine compressors, and prevent bleed air from getting hotter than 490 degrees Fahrenheit. Now let's see how the bleed air system operates during a typical flight. At ground idle, since the engine speed is low, the HSV is open and the system is running on 9th stage air. At these low pressures, the PRSOV is also wide open. The temperature is usually low enough that the PCCV is closed. At taxi, the high stage system continues to supply the bleed air. Depending on throttle setting, the pressure may rise above 32 psi. If this happens, the HSV will act to regulate the pressure to 32 psi. Again, depending on throttle setting, the bleed air temperature may rise above 390 degrees Fahrenheit. If this happens, the PCCV will open to keep the bleed air at 390 degrees or below. At takeoff and climb throttle settings, the engine speed is high. 5th stage pressure will increase above 32 psi so that 5th stage air flows through the check valve. The increased pressure will cause the HSV to close. 5th stage air will be above 42 psi and the PRSOV will modulate to keep the duct pressure at 42 psi. If the temperature is above 390 degrees Fahrenheit, the PCCV will open to allow cooling air to the pre-cooler. Typically at the beginning of cruise, system pressure will be such that the check valve will be open and the system will still be using 5th stage air. Depending on the altitude, the air may be greater than 42 psi, so the PRSOV will be regulating the pressure. Also, the temperature may be 390 degrees Fahrenheit or more, so the PCCV will open to regulate the temperature. During cruise, the pilots continually reduce throttle settings to maintain speed and altitude as the plane becomes lighter due to fuel burn. At some point, pressure may go below 42 psi. In this case, the PRSOV will be completely open. The PCCV will move towards the closed position as the temperature continues to decrease. If the airplane is heavy with a full load of passengers and cargo, the throttles will be set higher to maintain speed and altitude. In this case, it is likely that the 5th stage pressure will remain above 32 psi and the HSV will remain closed. If the airplane is lighter, the throttle settings may be lowered, reducing the 5th stage air pressure enough so that the HSV will open and the system will again be using 9th stage air. Note that depending on altitude, the HSV may open even at the beginning of cruise. In descent, when the throttles are brought back to flight idle, the 9th stage pressure will be below 32 psi, so both the HSV and PRSOV will be completely open. The temperature will likely be below 390 degrees Fahrenheit, so the PCCV will be fully closed. The Fault Isolation Manual, or FIM, has charts that compare normal duct pressure to N1 and altitude. By knowing the altitude, N1, and pressure when a fault occurs, you can reduce the scope of troubleshooting efforts. To learn how to use these charts, let's take a closer look at how they are built. At the bottom of the chart is a scale for engine speed. Moving to the right on the chart corresponds with advancing the engine throttle. On the left side of the chart is a scale for duct pressure. There are lines that plot bleed schedules or duct pressure readings you should expect to see at given engine speeds for given altitudes. This chart shows the pressure readings you should expect to see at sea level and 5,000 feet. There are also callouts that show the mode of operation the system should be in for each segment of those lines. This chart shows the bleed schedules for higher altitudes. Here's an example of how to use these charts. To make things easier to see, let's concentrate on the bleed schedule for 37,000 feet. The pilot has reported a low duct pressure of 25 psi while flying at 37,000 feet with an engine speed of 91% N1. If we plot this data on the chart, we can see that the duct pressure was lower than scheduled. We can also see that the system should have been on 5th stage air, controlled by the PRSOV. Since the HSR and HSV are not in control at this altitude and engine speed, they cannot be part of the problem, and you don't need to troubleshoot them. Low pressure in this example could be caused by a problem with a PRSOV or bar, so troubleshooting efforts should concentrate on these components. But remember, if the cooling system is not sufficiently cooling the bleed air, the 450 sensor will cause the PRSOV to reduce duct pressure to increase cooling. So you should also troubleshoot the cooling system, including the PCCV, the 390 sensor, and the 450 sensor. Another thing to keep in mind when using these charts is the pressure tolerances. Remember that when the system is operating in the regulated high stage mode, the HSV is regulating 9th stage air to 32 psi plus or minus 6 psi. And when operating in the regulated low stage mode, the PRSOV is regulating 5th stage air to 42 psi plus or minus 8 psi. Now let's see where to attach test equipment and some troubleshooting examples. Caution: make sure to turn off supply pressure before removing any pneumatic lines, hoses, or fittings. In order to see things more clearly, we'll be using an engine sitting in a cradle in the factory, rather than one hanging from a wing. Simple test equipment has been developed to aid in troubleshooting. The equipment consists of hoses, gauges, regulators, and fittings. You will also need a source of supply pressure. In our examples, we'll be using nitrogen. See your AMM for more information. You use the nitrogen and the test supply assembly consisting of hoses, pressure gauges, and regulators to simulate engine supply pressure in the system, and the control pressure gauges, hoses, and fittings to monitor the control pressure. Note that in some cases you may also need to monitor the movement of the valves. For our first example, note that the bleed air regulator or bar and the PCCV share the same supply pressure. On the left side of the engine, this T fitting takes air from the low stage duct and sends it to the bar and PCCV. To simulate the supply air to the bar and PCCV for testing, remove the supply line from the anti-icing duct to this T. Note that to save time in this video, all fittings have been loosened ahead of time. Then attach the supply hose from the test supply assembly at the T. To monitor the control pressure coming out of the bar, remove the control pressure line from the PRSOV and insert the PRSOV test assembly between that line and the PRSOV. Now open the regulator on the test supply assembly to provide the specified supply pressure to the bar. Check the control pressure from the bar to the PRSOV by looking at the gauge on the PRSOV test assembly, and observe the movement of the PRSOV as you apply pressure. If control pressure is low, there may be a leak or faulty part. To isolate the problem, begin with the PRSOV. Turn off the supply pressure. Then remove the gauge line from the PRSOV and cap it. Now reapply supply pressure. If the control pressure is normal, then the problem is the PRSOV. If the control pressure is still low, then there may be a leak in the 450 sensor or its sense lines. To isolate the 450 sensor, turn off the supply pressure. Then disconnect and cap its control pressure line up near the left side of the pre-cooler. If the control pressure is normal now, there is a leak in the 450 sensor line or its sense line in the pylon. If the control pressure is still low, the bar is not operating correctly, or there is a leak in the sense line. If no leak is found in the sense line, the bar is at fault. To troubleshoot the PCCV and the 390 sensor, you will need the PCCV test assembly from the kit. Turn off the supply pressure, then go to the right side of the engine. Find the test port on the control pressure line to the PCCV. Remove the cap from the test port and attach the hose from the PCCV test assembly. Then reapply supply pressure. If the pressure on the PCCV test gauge is low, this may indicate a leak or faulty part. To eliminate the 390 sensor as the source of the leak, disconnect its control pressure line up near the right side of the pre-cooler and cap it. If the control pressure is still low, the problem is with the PCCV or its control line. If the control pressure is now good, either the 390 sensor or one of its control sense lines is leaking. With good control pressure, you can use the needle valve on the test assembly to simulate the venting action of the 390 sensor. While you observe the control pressure, also observe the PCCV to see if it opens per the aircraft maintenance manual. If the PCCV does not open according to the AMM requirement, you must replace the PCCV. Note that for the sake of this test, if the PCCV opens to within 30 degrees of fully open, it is considered opened. A good reference to use is the inside of the screw head on the valve housing. To troubleshoot the high stage regulator, you will need the high stage test assembly. Recall that the supply pressure is taken from the high stage duct. Remove the supply line from the high stage duct then, using this special fitting from the test kit, attach the supply line to the hose from the test supply assembly. Remove the control line from the HSV and attach one hose from the high stage test assembly to the control line. And the other to the HSV. Note this is similar to what you did for the PRSOV. Now apply supply pressure to the HSR, monitor control pressure from the HSR to the HSV, and observe the movement of the HSV as you apply pressure. The HSV should open. If the pressure to the HSV is low, you will need to isolate the HSR and HSV to find the problem. Remove the test pressure line from the HSV, then install a test cap with a 32 thousandths of an inch hole in it on one end of the line. Note, this cap has a hole because the HSR needs a small amount of leakage in order to regulate the control pressure. The normal leakage in the HSV is usually enough for this. There are instructions in the AMM for making this cap. If the pressure is still low, the HSR is faulty, or there is a leak in the control sense line. And if the pressure is now correct, the fault is in the HSV. This ends our program, 737 Next Generation Bleed Air System Overview and Troubleshooting. With the information presented in this video, you should have a basic understanding of how the 737NG bleed air system works. Since the log report will tell you when a problem occurred, knowing what the system should be doing during that particular phase of flight will help isolate the fault and give you a better idea of what tests need to be run. You should also know where and how to attach the test equipment, run some of the more common tests, and interpret the results of those tests. Here are a few final thoughts. Keep in mind that this video is for training purposes only. Any pressures, temperatures, or other readings given are nominal and for the sake of illustration. For complete, accurate, and up-to-date information, always see the aircraft maintenance manual before beginning any maintenance tasks.